All right, in this video, we're going to go over the final review for AP Precalculus. This covers Units 1 and Units 2 through Section 2.8, Topic 2.8. So first, we have a graph from -5 to 5, and we're going to look for some different characteristics. So increasing. Okay, as we read the graph going from left to right, if the graph is going up, it is increasing. If the graph is going down, it is decreasing. So we're increasing, decreasing, increasing, decreasing, then increasing. Okay, so our intervals, we had 3 increasing intervals. The test is going to be multiple choice, so you just have to recognize the correct answer. So I'm going to write it using my inequality notation. So -5 to -3 for this one, from -1 to 1, and then again from 3 to 5. Okay, now it could be in bracket notation, so I'll do that for the second one just to show you different things. We're decreasing from here to here, so I could say that as -3, -1, and that's another way to show an interval. From 1 to 3 is my second one. Okay, on what intervals is the graph concave up? So our graph is concave down here, concave up here. There is no concavity if we have a line. So we're concave up from 1 to 5, concave down from -5 to -1. Okay. Next we're going to match. We've got 4 different graphs. Some of them are increasing, some of them are decreasing, some are concave up, some are concave down. So the statements we're looking at is the function increasing at an increasing rate, increasing at a decreasing rate. So the difference between those, we've already talked about increasing and decreasing. If it's increasing or decreasing at an increasing rate, that means it is concave up. If it's a decreasing rate, we're looking for the graph to be concave down. Okay, so here a function increasing at an increasing rate is it's increasing and concave up. So that's going to be that one. Increasing at a decreasing rate, so still increasing, but the graph is concave down. Decreasing at an increasing rate, so we're looking for decreasing but concave up. And decreasing at a decreasing rate, concave down. Now we're going to describe end behavior. So this is going to depend on the degree and the sign of the leading coefficient. So I'm going to go through each of these. This first one is an odd degree because it has a degree 3, and it has a positive leading coefficient. So the graph of an odd positive is going to look something like that. When we write our end behavior, we always write the limit as x goes to -infinity and the limit as x goes to +infinity. Okay, so for this one, as I go to -infinity, my graph is decreasing without bound, so this goes to -infinity. Here it's increasing without bound, so it's going to +infinity. My second one here is an odd degree, because it's degree 5, but the leading coefficient is negative. So that's going to make the graph look more like that. Okay. So write the limit statements. For this one, as we're going to -infinity, it's increasing without bound. As we're going to +infinity, it's decreasing without bound. Okay, this one is an even positive, which means our end behavior is the same at both ends. So for this one, for both, we're going to infinity. And then the final case is an even negative. So my graph will look like that. Okay, so for both -infinity and +infinity, we are going to -infinity. Next, we have the average rate of change over different intervals. So the average rate of change formula, absolutely something you need to know, but you've known it for a very long time. It's essentially just the slope. So f of b minus f of a over b minus a. Okay, so if I'm doing this formulaically, we've got f of 7 minus f of 0 over 7 minus 0. So if I go to my graph, f of 7, now here I've got an open dot and a closed dot, and when it's like that, we evaluate at the closed dot, which is going to be at 5. The function value at 0 is 2, so we get 3 over 7. Now what you could do is go from this point to the point on 7 and literally go using your slope. Okay, let's do another one. So 4 to 9. So f of 9 minus f of 4 over 9 minus 4. At 9, we're at 4. At 4, we're at 2. So we get 2 over 5. And again, you could start there, go up 2 over 5, and do it like that. You could draw the line even. Okay, so f of 8 is 6. F of 5, again, we've got a situation where we have to pick the right one, which is going to be at 1. We get 5/3. Okay, last one, f of 10 is 2, f of 6 is 5, so we get a negative 3/4. Okay, we have a polynomial and we're trying to find what the possible equation would be here. So, looking at our characteristics, number 1, I have 3 zeros. I have a 0 at negative 3. We have a 0 at 1, or negative 1, but notice that it just touches and bounces off. That means this has an even degree multiplicity. Okay, so at a minimum, it has a multiplicity of 2. And then we have another 0 at 2. So if I write this formula, we're going to have, if negative 3 is a 0, then x plus 3 has to be a factor. If x equals negative 1, we're going to have an x plus 1, but we're going to square that one because it has a multiplicity of 2. And then we'll have x minus 2. Now, something we want to be careful of, we've established the zeros. This does have an even degree polynomial, which is good, but we want to pay attention to the end behavior. This one's going to have a positive leading coefficient, but had the whole graph been flipped, we would have all of this, but then we'd need to make it negative. With complex zeros, if one complex value is a 0, its complex conjugate is also. So if you have a plus bi, its complex conjugate is a minus bi. So if negative 4 minus 2i is on a 0, then negative 4 plus 2i is a 0. If 3 plus 5i is a 0, 3 minus 5i must be a 0. And if 6i is a 0, negative 6i is also a 0. Okay, next I have this graph here, and we're going to decide if we know 2 minus 3i is a 0, what is the least possible degree? So some features, we're going to look at the zeros, but I also want to look at this end behavior, which tells me it's going to have to be an odd number, because this models the end behavior for an odd polynomial. So for the zeros, if 2 minus 3i is a 0, then 2 plus 3i is a 0. We have x equals negative 3 is a 0. X equals negative 1 is a 0, but it has at least a multiplicity of 2. Same thing with 2. Okay, so if I add that up, we've got 1, 2, 3, 4, 5, 6, 7. So the least possible degree for this is 7. Next, we're going to identify the extreme values, extrema. So those are the maxes and mins of the graph, and they can be either local or absolute. So characteristics of the graph I want you to pay attention to. Here, we have an arrow, which indicates that this is going to continue down. This has an end point, which means it stops there. So local minimums, actually, let me just label them on the graph. Okay, on our graph, we have a maximum here. We have a minimum here, we have a maximum here, and this end point is considered a minimum. Okay, so all maximums are local, or minimums are local. So we have a local min at x equals 2 and at x equals 6. The local maxes, here and here, at -4 and +5. Absolute, we're looking at those values and seeing if they are the smallest value or the biggest value. For the minimum, if we weren't paying too much attention, we might say that's an absolute minimum, but because this is going to continue to go down, there's going to be values lower, which means we have no absolute min, but we do have an absolute max. All right, next, our table of values. We're determining whether these are linear or quadratic, and we're basing this on the rate of change. So one thing I'm going to look at here is my input values are in equal length intervals. So no matter what, the denominators are going to be the same. So I really just want to look at the numerators for the rates of change. And that's going to come from the difference in the y's over the difference in the x, but I'm not going to worry about that because it's all going to be 2's. So here, if I look, that difference is we're going up 2, up 2, up 2, up 2, up 2, which would make this linear. Okay, and we're going to write the reason based on the rates of change, but keep in mind this will be multiple choice, so you just want to pick the right one. So our justification is the rate of change over equal length input value intervals is constant. The second one, we're going down 2, down 4, down 6, down 8. So there's certainly a pattern there, but it is not linear because those are not constant. But if I look at here, we're going down 2, down 2, down 2, which means there is a constant for the rates of change. So this one's going to be quadratic. And then again, I'll write out our explanation. Okay, so our justification here is the rate of change over equal length input value intervals is linear. So the difference is if it's constant versus linear, meaning these form a line, they go up by a certain amount. Next, we get into rational functions. So the first thing we're going to look for is horizontal asymptotes, and that's going to be determined by the degree of the top and the bottom. In this first one, the degrees are the same. Okay, which means what's going to take over is the leading coefficients. Okay, so as we go to infinity, this graph is going to go to 3/2. Here, my degree is bigger on the top. I'm going to abbreviate here. The numerator is greater than the denominator. If that's the case, there is no horizontal asymptote. There could be a slant asymptote, but we're not worried about that right now. Here, if the degree is bigger in the bottom, then we do have a horizontal asymptote at 0, because as we go to infinity, this denominator is going to grow way faster than the numerator. Okay, so if you want to see doing those, here I have the same degree, so it's going to be -10/2. So I'm going to have a horizontal asymptote at -5. Here, if I multiplied this through, we'd have a degree 4 over a degree 2, which means there's none. And then here my degree is bigger in the bottom, so we have a horizontal asymptote at y equals 0. Right, next I've got another rational function, and we're looking at the vertical asymptotes and holes. So the first thing we need to do is reduce this down. Okay? So here I've got an x to the 7th to the 5th on top, x to the 7th to the 4th on the bottom, so that can cancel. That's going to become a 1. Here we've got 3x plus 5s on top and 5 on the bottom. That's going to become a 2. So I can rewrite this equivalently as x minus 7. Guess I don't really need the parentheses. X plus 5 squared. So in this, anything that makes the denominator 0 is going to be either a whole or a vertical asymptote. If when I cancel it, it's no longer in the denominator, like the x minus 7, that makes it a whole. Okay, and it's going to be the opposite sign. So if I plug in a 7, I'm going to get 0. It's going to give me a 0 in the denominator, but I can remove it with that simplifying. That should be x equals. And then my vertical asymptote, even after, if we simplify it down as much as we can, but it still makes the denominator 0, that's the location of a vertical asymptote. Next, we're going to read the graph and answer some different limit statements. So this first one is saying, what is the limit as x goes to infinity? So we're looking at, as it keeps going out here, what's going to happen? Well, it's going to approach this vertical or horizontal asymptote. So it's going to 2. As I go to negative infinity, it's also approaching negative 2. Negative 2. Even though it doesn't actually reach there, but the limit is just where it's approaching, not necessarily where it's at. Next, we're looking at negative or positive 1. Okay, 1 is the location of a vertical asymptote, and different things are happening on the different sides of the graph. So we have to pay attention to the little notation. Here, this is 1 from the negative side. This is 1 from the positive side. So 1 from the negative side is going to positive infinity. 1 from the positive side is going to negative infinity. Okay. And then as we approach 3, we have a hole here, but the limit still exists because we're still approaching the same thing from both sides. So both of these, both from the positive and from the negative, are approaching negative 3. Next, I've got some rational inequalities, and we're solving them for different values. So here I want to know when this is greater than or equal to 0. So I like to use number lines. Okay, so I draw a number line for each of those factors, and then I do another one for the function in general. We have 3 critical points, values that make this 0, and that's going to be at -4, 0, and 3. And then I'm going to put the corresponding value on the specific number line. Okay. Before I even do any of the analysis, here I'm going to put a 0 at 3, because if I plug 3 in, I get 0. But I'm going to put x's here, because no matter what, that's not going to be included, because those are going to be both locations for vertical asymptotes. Okay. You can pick a test point or think about it graphically, but if I plug in a number less than 3, we're going to get a negative number. If I plug in a number bigger than 3, we're going to get a positive. Same here. And same here. That may switch if you have like a 3 minus x. It might be different if something's squared, but these are all just linear. Then we have this divided by this times this. So we'd have a negative divided by a positive when I multiplied those, which is going to be negative. Here I'm going to have a negative over a negative, which is positive. Here I'm going to have a negative over a positive, which is negative. And then we've got a positive over a positive, which is positive. So then we pay attention. We want it greater than or equal to 0. So that's where our values are positive or 0. So in this case, we have from -4 to 0, non-inclusive because we can't include those endpoints. And then when x is greater than or equal to 3, because it is equal to 0 there. Okay, here I just need 2 number lines. Okay. So here we've got zeros at -7 and 3. They both go negative to positive. So here I get a positive, a negative, and a positive. In this one, I'm looking for when we are less than 0, so that's going to be here between -7 and 3. And I don't include either because it's simply just less than. We'll write an equation for a rational function in factored form that has a whole at x equals 8 and a vertical asymptote at x equals -1. We'll call this guy f of x. Well, if x equals 8 is a whole, then we have to have an x minus 8 and an x minus 8 in the denominator. And then if we have a vertical asymptote at x equals -1, then x plus 1 needs to be a factor in the denominator with no corresponding one in the numerator. Next, we have some transformations. So we need to recognize what's happening, and then we're going to graph the corresponding graph. So this is f of x, and f of x plus 3 minus 2 means we're going to the left 3 and down 2. Okay, so we're going, taking this point, go left 3, down 2, left 3, down 2, left 3, down 2, left 3, down 2. Or you can just kind of reconstruct what is already there. But again, this will be multiple choice, so you just have to pick the right one. Here we've got a negative and a 2. The negative is going to reflect it in the x-axis. And then we have a vertical dilation of 2. Okay, which means all the y values are going to get doubled. So I'm going to take each of these points, reflect it over, and then double it. Reflect that over, double it. Reflect that over to 3, and then double it to -6. Reflect that up to +3, and pull it up to +6. If we're multiplying on the inside, this is a horizontal dilation. Okay, by a factor of 1/2. Okay, which means it's going to get compressed horizontally. So this point out at -3 is going to get squished in to -1. -1 is going to go to -1/2. This point at 3 is going to go to 1.5. And this point out at 6 is going to get squished into 3. So it has the same range of values, the same y values, but our x values get compressed. And then this last one, we're going right 2 and up 1. Right 2, up 1, right 2, up 1, right 2, up 1. And then right 2, up 1. Okay, so we have a function that has a domain of -4 to 6 and a range of -2 to 10. We're going to find the domain and range for g of x after some changes. So let's talk about the changes. So here we've got stretched vertically by 2. It's going to be moved to the right 3 and up 1. Okay, so for my domain, which starts as -4 to 6, the only thing that's affecting the x values is this right 3. Okay, so that means these are all going to be moved to the right 3, so -4 is going to go to -1, and 6 is going to be at 9. For my range, we're starting at -2 to 10. We're first going to stretch it vertically by a factor of 2. which is going to make this negative 4 and 20. And then it's going up 1, which means this is going to be at negative 3, and this will be at 21. Okay, we're going to do that same thing here. Okay, my range, which starts at 10, the only thing that's going to affect that is that it's going down 2. Subtract 2. And we've kind of been doing this along the way, but we're going to do it again. Describe the transformations. So this is going to be a vertical dilation. I'm just going to abbreviate. By factor 1/2. We are going, I'm just going to call this a horizontal translation. I've been more specific, but it's going to be a horizontal translation of negative 9. So sometimes you might see it as left 9, sometimes you might see it as negative 9. And then a vertical translation of negative 17, or going down 17. Here I have a vertical dilation with a factor of 8. Here I have a horizontal dilation with a factor of 1/3. It's always the reciprocal when it's on the inside. The function h is constructed by applying the following transformations. A horizontal dilation by a factor of 1/2, a vertical dilation of 4, a horizontal translation negative 3, and a vertical translation of 5. So h of x is equal to, our vertical dilation was 4, our horizontal was 1/2. So we're going to have a 2 on the inside, and then we're going to use parentheses for the horizontal translation. If that's negative 3, this is going to be a plus 3. And then a vertical dilation of 5 will make that a plus 5. Okay. So geometric sequences. So geometric sequences are when we're multiplying by some common ratio. We're going to write an expression for the nth term, which in general, and this is absolutely something you need to know, is gn equals gk r to the n minus k. So for this, we need to find out what our kth term is. So here we want to center it at this point. So that's g3 equals 4. So 3 is my input, that's going to be the k. My 4 is the output, that's going to be your gk. My common ratio, so we're going from 1 to negative 2 to positive 4 to negative 8. So my common ratio is going to be negative 2. So my equation is going to be 4 times negative 2 to the n minus 3. So my k is 3, my output at 3 is 4, and then we have our common ratio. Next we have an arithmetic sequence. So the general formula for an arithmetic sequence is AK plus D n minus K. Okay, so again, we have to find our D and our kth point. So if this is B, that means A5 equals 4. So 5 is my input, 4 is the output. My common difference, so we're going down 1 over 2. So if I were just to go over 1 unit, we're going down negative 1/2 each step. So we're going to have our output value 4 minus our common difference 1/2 and minus the input of 5. So this is like x and y. It's just k and ak. So here I have two table of values where we're trying to determine if they're linear or exponential. So this is similar to what we did with linear and quadratic. The difference is, are you adding or are you multiplying? So here we can see we're adding to, and so on. This one, I'm multiplying by 1/2. Okay, and the other thing is these are equal length input values. Okay, so this one is linear. This one is exponential. And then we're going to write the justification using the relationship between the input values and the output values. Okay. So our explanations start off the same. They both start over equal length input value intervals. The change is here. The output values change at a constant rate versus the output values change proportionally. Okay, now we're going to determine if we have exponential growth or exponential decay based on our output values here. So if you're looking, we're multiplying. And here from 1/2 to 3/2, we're multiplying by 3, and so on. So the base of this exponential function is going to be 3, which means we have exponential growth. Okay, because b is greater than 1. Here we're going from 1 to 2/3 to 4/9 and so on. So we're multiplying by 2/3. So my b is 2/3, which means we have exponential decay. And our reason is because the b is between 0 and 1. Right, more end behaviors. Okay, so again, we are looking at as our function goes to negative infinity and as it goes to positive infinity. So this one, as we go to negative infinity, it's increasing without bound. Here it's approaching 0. This one, as we go to negative infinity, it's approaching 0. As we go to positive infinity, we're going to negative infinity. Next, we're going to look at if the graph is increasing, decreasing, or concave up and concave down. So we have to use our knowledge of what our exponential functions look like. This one is going to be exponential growth, however, we're reflecting it. So exponential growth would look like this. So it's going to be flipped over and it's going to look like that. Okay, so this one is decreasing, concave down. Here, this is just exponential decay, not flipped over, so it is decreasing and concave up. Okay, we're going to rewrite 8 raised to the x thirds in the equivalent form ab to the x. So we just want an x here. We don't want any coefficients. But I can use my properties of exponents to rewrite this as 8 to the 1/3 x. And then 8 to the 1/3 is the cubic root of 8, which is 2. Okay, so the number of viewers for a new show on Netflix is increasing by 30% each week. There were initially 10,000 viewers. Write the exponential function that measures the number of new viewers where t is measured in days. Note that there are 7 days in a week. So we're going to have our starting value of 10,000. Okay, the base, we're going to start with 1.3, but it's that 1.3 per week. So if we're looking at each day, what portion of this are we going to have? It's going to be to the 1/7, because we get 1/7 each day that week. So this is going to be, I guess f of t is 10,000, 1.3 to the t over 7. Okay, next we have some residual graphs. So a set of data was created, used to create a linear, quadratic, and exponential regression. We have the 3 residual shots, so we want to pick which one is the best model. Well, what we're looking for is no clear pattern. Here we have a pattern. Here we have a pattern. Here we have no pattern. No clear pattern. Okay, which means quadratic is the regression for us. We've got 3 equations and we're going to do some compositions. So g of f of x. Okay, so we're going to take this equation and plug it in for the x's here. Okay, then we're going to need to simplify this. So I need to factor that out. Okay, and then distribute the 2. And then combine our like terms. So negative 21x, and then 8 and negative 6 is 2. Okay, we're going to do the same thing with h of f of x. So h of 3x minus 2 is going to be the square root of 3x minus 2 plus 1, which would be 3x minus 1. And then our last one, f of g of x, so we'll have 3 times 2x squared plus x minus 4 minus 2. So we get 6x squared plus 3x minus 14. Sorry. Next, we're going to graph some inverses. So when we graph an inverse, it's a reflection in the line y equals x. Okay, or we pick points. So this one, like I've got a point at negative 2, 4, which means I have a point at 4, negative 2. And then I've got a point at 2, 4, negative 4. So we're going to have a point at negative 4, 2. And then it's going to be that same shape, just sideways. Okay. And then here, I'm going to switch my x and y coordinates. So negative 3, negative 5 is going to be negative 5, negative 3. 0, negative 2 is going to be negative 2, 0. 1, 3 is going to be 3, 1. And then 4, 4 is going to be at 4, 4. Okay, next we have the calculator questions. So we're going to look at this function, and the first question we're asked is, what are the zeros of the function? So I have it in my graphing calculator, and I'm going to graph it on just a standard window to start. And there we got it. So we have 3 zeros, here, here, and here. So to calculate those, you go to calculate 0. Okay, so we're going to go below it, hit enter, go above it, hit enter, and then our guess. Okay, so our first one's at negative 0.484. So then we'll do the next one, calculate that 0. Left, right, guess is at 1.431, and then the last one is at 2.584. Okay, next we want to know on what values it's increasing and decreasing. So it's increasing, decreasing, increasing. So what I need to do is find the max and min values. So I'm going to calculate the maximum. It's going to be the same questions, left bound, right bound, guess. So we get that maximum, so it's increasing to that point, then it's decreasing to the minimum, then it's increasing after that. So we'll find the minimum. Okay, so we're going to calculate the minimum. Okay, and that minimum value is 2.072. Okay, so I'm actually answer this question and then I'll come back to this one because we just found our maximum and our minimum location. And then again, we said it's increasing to that max, then decreasing to the min, then increasing afterwards. So it's increasing from negative infinity to that maximum value. And then from that minimum value to infinity. And then it's decreasing in between them. Next, we have some data, and we're going to make an exponential regression and use it to predict what's happening at 2.1. So we want to enter in the data, and you do that with stat edit. Okay, I've already put my data in here, so we've got our x's and our y's. Then you're going to do stat calc and go down in this menu until you find exponential regression. So list 1, list 2, and we want to store this. Okay, so we're going to store it in y1 and then calculate. So that's our regression. Okay, but I'm not going to plug it into that. I'm going to use my stored value. It's stored in y1 and then plug in 2.1 to get my answer. So G of 2.1 is 11.566 if we round. So this is your final review for topics 1.1 all the way to 2.8.